Hello and welcome to part 3 of the R training course. Yesterday we talked about opening files and spreadsheets and writing data from within R. Today we are going to talk about some of the command and control structures available in languages. I think many of you have probably had some prior exposure to BASIC or C programming even, or Pascal. If you haven't, then maybe these terms might be coming to you for the first time. So I'll try to explain all of that as we move along. Thanks as always to Diplomix for putatively funding this training course. We'll be using just base R again. If you're using RStudio, that should be just fine. The examples all appear in this text file that is available from the URL attached to this YouTube video. Great. So we are going to talk about executing conditionally, iterating through loops, and creating functions. So specifically we'll cover if and else, for looping, while looping, one of my favorite functions, subset, just because it's awfully useful. And at the end we're going to define our very first function in R. So I think that will make it clear how you can save retyping functionality that you use a lot. Now, as I mentioned, pretty much all programming languages use looping to some extent. And looping is just iterating. It's redoing a set of operations with a slightly different input each time. So we'll try to get through this bit by bit. We're going to start with a for loop. Very frequently, we need to execute the same code multiple times, but in each case we want to increase the value of some variable or decrease the value of some variable. So I'm going to copy that text and now paste it over here. It's important that you copy all the way down to that bottom brace. If you just type for I in 1 to 10 with the open brace, the software is not going to keep going because it expects you to have closed that brace before it's told to execute it. You could type this a little differently. You could say for I in 1 to 10 cat I squared, new line, and then close it like that. See, that's going to give the same output, but here I've just unpacked this one line to occupy more lines. So let's try to walk through this. First off, we've got that little bit about I in 1 to 10. So the series operator expands 1:10 to the values 1 through 10. It's a vector, in other words. So I is going to start its way through here. On the first execution of the code, I is going to be equal to 1, then I is going to be equal to 2, I is going to be equal to 3, and so on. It's also possible to do reverse series like that. You could specify the larger number first. I think there are ways to do stepping 2 at a time, for that matter. So you have you're going to have some way that you specify how many times this runs. In effect, 1 through 10 acts as a set, and the code is going to execute for each member of that set. Now, I note that we've used a function for the first time here. I think you saw for in some of the code yesterday, just briefly. That's what allows us to iterate through all members of that set. But I don't think you've seen the cat function before. Cat is very useful when you're trying to spit out a bit of text to the screen. There are also comparable functions for outputting a string to a file, for example. You could write to the file instead of writing to the screen. But as usual, we're going to pass to this function whatever appears between these parentheses. Now, we've seen the plus and the minus and the division and the multiplication signs, but I don't think you've seen this caret used before. Caret is just letting us raise a number to a power. So in the first pass, 1 raised to the second power is 1. 2 squared is 4, 3 squared is 9, and so on. Before, when we created a tab-separated values file, when we were outputting that result using the write table function, we specified that we wanted to separate values on a \t character. You remember seeing that? \t at the time, I said, was a tab character. Here, we are using something called the new line character. The new line character. So the new line character just means that when you're done writing whatever I squared is, go to the start of the next line instead. So we could change that pretty easily to \t. And how is the result different? Right, so now we have tabs separating the square values, and where did our blinking cursor go? It's way off the right edge of the screen at the moment, so I can hit enter and I'm back. So in our original form, each square gets put on its own line because of the new line character is printed after it. In the second example, the tab character was printed after each line instead. So those are just some basic things to know that pretty much all computer programming languages use in some way or another, so it's good to know about them. All right. Now, I talked about the curly braces here, but I didn't really define what those are. So curly braces are very frequently used in lots of programming languages as a monolithic section of code, that this is this whole block runs as one thing. So in this case, we have a for loop, and within the for loop, we're going to do some stuff. So all of that stuff needs to be held within curly braces. I could have continued on, I could have catted the square on this line, and I could have catted the cube on the next line. That would be really easy to do, right? Just I up 3, new line, like that. So I might have, for example, printed the square on one line and then the cube on the next line. But in this case, I don't want to modify my code here. But all of that, because it fell within the curly braces, was going to be executed every time we did a round through this iteration. Okay, generally speaking, programmers like for code to be inset, to be indented, to reflect that it's part of one of these curly brace sections. So by adding a couple spaces here, I make it clear that this cat function is dependent on the for, that it's part of this curly braced section. Okay, now it might seem that the only way to do to use for is with numbers, but it works with any kind of set, really. So I could say that I want to use letters. Now, letters is a predefined function for us. Letters is always equal to all of the letters available in this alphabet. So if I run this code, it's going to cycle through each of the letters contained within letters and then output that to screen, followed by a space. So a space is actually used by just a space. We don't have to backslash it or anything like that. \t and \n are special characters, space is not. So you might ask a complex question here. How do you print a double quote, considering that you have to enclose it in double quotes? So in a case like that, it is again something where we need to use a \/ to indicate it's a special character. But in this case, we just wanted to separate each of the letters from each other by a single space, and we can just do that by indicating that. So cat is first going to output the current letter, and then it's going to output the space. It is also possible to do things like creating, say, a factor. I'm going to create a factor called fruit. Fruit is equal to a factor of a string bananas, oranges, and apples. And remember, I opened 2 parentheses, so I got to close them both. All right, so did fruit create correctly? It did. So if I say for fruit, oh, sorry, we'll just call the looper thing f. For f in fruit, cat f, comma, quote. All right. So the only part that's going to execute every time is to cat whatever f we're on, and then a space. And here we see that's exactly what happened. So we often think of for loops as using integers for counting, But you can use numbers drawn from any set of things, including a factor like this. I see folks are still looking at the screen, so I don't want to glip away. But in every case, this is one of these commonalities that we have with the Python programming language. Python's really good at making use of lists of different elements and cycling through each of the elements in that list. Here we have very much the same behavior from R. Grand. So let us now look at if. We're going to combine it with a for loop in this case. So I is going to iterate through the members of 1 through 10. And then we're going to try to determine whether I is currently odd or I is currently even. And I'm going to do a little bit of odd math here. I'm going to use the modulo operator. Modulo is a term that a lot of people they raise their eyebrows like, why are you inventing new math here? But I'm not. Because you'll remember that when you were back in elementary school learning how to divide numbers for the first time, that is an elementary school thing, isn't it? Yeah, all right. So elementary school, if you're doing division in elementary school, they usually don't have you break out decimal points and say 5 divided by 2 is 2.5, right? You might stop at the 2 and say, well, 2 goes into 5 2 times, and there's a remainder. Remember that? Modulo is remainder. All right, so the light is dawning. This is grand. So we're asking, is 1 evenly divisible by 2 or not? What is the remainder if we divide 1 by 2? Anyone know what that is? 1 divided by 2 goes in 0 times with the remainder of 1, right? So the value is going to be 1 for that. So I'm going to run this code first, and then we're going to try to take it apart. It's not a lot of code there, but there's a lot of interesting stuff going on. So we start by saying the value of 1 modulo with 2. We're going to look at the value of 2 modulo with 2. The value of 3 modulo with 3. The value of 4 modulo, oh goodness, I said 3 I meant 3, 2, sorry. And then I wanted to do 4 modulo 2, I'm sorry. Ignore that one right there. Okay. So what we see is that this number is alternating every time. It's 1 when we have an odd number, and it's 0 when we have an even number. 2 modulo 2, there is no remainder when you divide 2 by 2. There's no remainder when you divide 4 by 2 or 6 by 2. So we're taking advantage of that to create a value that's either 0 or 1. But now I've done something really a little tricky with this. Remember that we have this if business in here surrounding it. And I note that this if is actually spanning 2 lines. Because there's not just an if clause, there's an else clause as well. Whenever you ask an if question, it's either a true outcome or a false outcome. This is one of those cases where we have a Boolean value. So if the number is positive, if the value is 1, if there is a remainder, then we want to output that this is an odd number. If I say if 1, sorry, I got to remember my language here, cat. You see that? If 1, then output yes. If 0, then cat no. Sorry. So why did we get an output in the first case but not in the second? Because to a computer programmer, something that seems completely self-evident is not going to be clear to people who've never programmed before. To programmers, the value 1 is the same thing as true. If I say if true, cat yes, I'm going to get an output. If I say if false, cat yes, I get no output. So to the computer, 1 and true are the same thing. 0 and false are the same thing. So in this case, I have coerced this value of I into a 0 or 1, asking whether I can or cannot divide it without a remainder. So this is not a lot of code, is it? But there's a lot to it. We're turning an integer into a yes or no answer by moduloing it with 2. We're going to use that to decide whether we output odd or even. That was part of what was missing from this business right here. Let me start with if true cat yes, else cat no. Okay. If true cat yes gives us yes. If false, we cat no. You see that? The only thing that's different between this line and this one is that I've changed what value we feed to the if. In the true case, the first thing happens. In the false case, whatever follows the else happens. Do we see that? So else is only going to happen if the condition you pass to if is false. Now, I don't want to blow up anybody right now, but I would point out that you can frequently use nested structures, which is to say multiple layers of if. You can also use compound structures. So let me try a biologically related one. My height is let me see. Am I feeling tall today or short? Tall. All right. I am 69 inches tall today. All right. My weight. I've gained some weight. I don't remember what I weigh in pounds anymore. What's that? I'm skinny today. What do I weigh in kilograms? 55. Oh, come on now. I'm at least 60 kilograms. I'm at least 60 kilograms. All right. So now we have two numbers. Again, we need to create a Boolean outcome from it, a true or false decision. Okay, so let's look at a compound. I'll try to remember the syntax for this. My R is a little rusty, frankly, but we'll just try it. So I could say if height is greater than 50, cat, how's the weather up there? Okay, great. So that's one condition. Oh, sorry, I need to get to a clear screen. Okay, now I'm going to add another condition. I'm going to try to remember how to do this. Weight. Let's say if my height is less than 70 inches and my weight is greater than 70, I'm going to cat, have you talked to your doctor? Boy, I'm being really insensitive in my my language to my software today. All right. So this gave no output. Does anyone see why? Okay. So first off, is height greater than 70? No, it's currently sitting at 69. Is my weight greater than 70? No, weight's currently sitting at 60. Okay, so let's try more realistic numbers. Okay, I'm now going to say I'm actually a little taller. I'm now 71 inches tall, and I've been eating a lot of jelly beans lately, so I'm going to set my weight to 80 now. I'm going to rerun that same line. Have you talked to your doctor? Okay, so now we see that these two variables both have values on which this if depends. If I change my weight back down to 60 and I rerun that line, no output. Both of those conditions must be true in order for the overall expression to be true. Okay, great. Now, that's not the really mind-blowing stuff. The really mind-blowing stuff is if you start making an if that depends on the result of a prior if. So if I say if weight is greater than 50, and then inside that block I ask another if question, this time about my weight, for example. So I might say, if my weight is less than 50, do whatever in this block. If inside that block I then ask, is your weight below 40? Is your weight below 30? I can keep adding new layers to this. And finally bracket where this person fits within the range, right? So nested ifs is what happens when you have these ifs at multiple levels. I'm not going to do an example of that on screen, but I just want to point out that you can go to a lot of complexity with this. In fact, a lot of the machine learning tools that we use, like random forests and decision trees, are essentially these nested if statements about a set of biomarkers. So these have real application in biomedicine. All right, I went a lot further with that than I really needed to, but I hope that that much is clear. So to use a couple more examples of the modulo operator, what is the remainder when we divide 15 by 3? 0. It's 0. It goes into it 5 times and it goes into it evenly, so there's no remainder. 15 modulo 4, on the other hand, gives a remainder of 3, right? What happens if you say, if 3 cat true? Isn't that weird? I just said 0 is false and 1 is true, but what about all the other numbers? Right, that's messy. Generally speaking, computers will try to do something reasonable if you give them unanticipated output. In this case, any positive number is treated as a true value. What about a negative number? Negative numbers are also true. But is a 0 true? No. 0 is always false. So maybe any value other than 0 gets called true. That's a language-specific behavior. Okay, so we're now going to move on to while loops. While loops are a little bit more flexible than our for loops. Remember that when you set up a for loop, you have to specify in advance all the different values that the index variable can take on. We used like 1 to 10, for example. But sometimes you're not sure how many times you're going to need to iterate through that section of code. And for that, while is your best friend. Here we have an example of an extended section of code. We have 3 lines that are going to be executed every time this loop runs through. So I'm going to start by just running this. Okay. Right. So x starts with a value of 0. Square starts with a value of 0. So we call that initializing a variable, setting its value at the start of things. And then we're going to do our while loop. And we see that while is only going to run so long as square is less than 100. So what if I started by saying square equals 200? Would this code inside ever execute? It would not, right? So for any iteration of while, we need to satisfy the condition of that while. In this case, that square is less than 100. I'm going to point out something else that's really awkward that happens to programmers fairly a lot, and it's worth talking about, which is an infinite loop. What if this function never sets the value of square? What if it never changes what the value of square is? This loop just keeps executing and executing and executing because the value of square never changes. So you can see that here, at the second line, I've specified that square is always going to be equal to x squared. But x itself has got to reach what value before square is at least 100? 10. Right, so just because I set the value of square doesn't mean it will ever reach 100. I actually have to increment x in order for that to happen. Okay, we're using a really common bit of code here, saying x equals x plus 1. This is called incrementing x. Whatever x's value was before, we're going to add 1 to it and shove that back into x. I'm going to tell you a joke about, I'm going to tell you about the sense of humor that programmers have. For a very long time, people had been using languages like Pascal and BASIC, where you used syntax very much like this, to say x equals x plus 1, and that's how you do it. So incrementing was like that. However, when Kernighan and Ritchie created the C programming language, they said everyone's incrementing this way all the time. We should surely have a faster way to type, I want to increase this number by 1. So they came up with an operator marked plus plus. So if you had some number and you wanted to increase its value by 1, you would just say, j plus plus, for example. When the guys came along who wanted to create the C++ programming language, they had to come up with a name for what their software was, how their language was distinctive. And they said, well, it's like C, except it's one better. So they called it C++ to reflect this programming convention. Programming people are weird. You just gotta know that going in. All right, so we start with x at 0. At the start of our loop, we increase the value of x by 1. We then compute its square to be 1 as well, because x is currently valued at 1. We cat its value out. So why is there never a time when it cats 0, 0? Why does it not cat 0, 0 at some point? Because we've already increased the value of x. We've already increased the value of square at the time that we write the first line. If I had reordered this to have cat at the top rather than x equals x plus 1, 0, 0 would have appeared, but it doesn't here. Okay, right. What is the current value of x and square? 1 or 2? Yes, what is the current value? If I type x right now and hit enter, what's going to result?
10.
It's 10. It's because the software has already run through this loop 10 times. You remember the last value that it outputted down here, it showed that the current value of x is 10 in the 10th iteration of this loop. Square is set to 100. Okay. So, while lets us iterate through a block of code some undefined number of times until some condition is met. Okay, right. I just want to say that one of my first programming jobs came after I finished my undergraduate degree at the University of Arkansas. I was working for a transport company in near Liberty, Missouri, a place no one will probably have heard of, but that's okay. So I was there working at this transport company where a self-taught programmer had written the entire database architecture of this transport company. She taught herself how to program while she was working at this company. And for 10 years, she had built this massive structure of a database. And I want to tell you that I, as an intern, inherited all of this code because she left the company 1 week after I arrived. All over her code, I found code that didn't say while square equals less than 100. It said while true. What is that? Under what conditions does this condition give anything other than true? This is by definition an infinite loop. Inside the code, she had created, do some stuff, and if a certain condition was met inside this loop, then she would issue a break command, at which point the loop would stop running. I chased my tail through her code all through the summer after I graduated from college. I gotta say, it was not relaxing. So, anyway, good practices, bad practices, programmers come in all stripes. Okay. Yes.
How do you erase that? Because when you make a mistake and you're trying to erase it.
Oh, so I actually used a bit of Emacs shorthand, I'm sorry. So yeah, when you have a bunch of text on screen, you could just hit enter and it gives you an error.
Yeah, it gives you error.
Yeah, but I went to the start of the line with Control A and then hit the kill button, which is Control K.
Or Control A and Control K.
Yeah, I'm sorry, that's a really obscure way to do it. It has to do with the fact that I use Emacs all the time, and so that's kind of my default behavior. I'm sorry, Emacs people must be forgiven, it's true. I just want to point out that Emacs is one of the very few text editors out there, that's what the software is, that has a built-in psychiatrist. Really? Look, I'm going to type Alt-X and now doctor. I am the psychotherapist. Please describe your problems. I am not sleeping well at night. Why do you say you're not sleeping at night? Does anyone recognize this software? This is Eliza, one of the first artificial intelligence attempts. It's built into every copy of Emacs, just because. Because I like talking about my problems. Is it because you like talking about your problems that you came to me? Yes, nobody listens to me. Earlier you said you like talking about your problems. It's not a helpful psychotherapist, but there you have it. Anyway, like I said, computer programmers have weird senses of humor. If you don't believe me, look up the flight simulator built into Microsoft Excel. Really? Really? All right. Sorry, I'm talking a lot of nonsense today. I'm going to run this little bit of code because I needed to have a little mock-up data to work with. So I'm just going to run all of this. You've seen the runif command a few times now. We use it for sampling numbers from a uniform distribution. And we've created a data table, a data frame from it called experiment table. So if I look at exp table, I have that. All right. Data, why did I do that? Oh, sorry. Summary experiment table will probably look a little cleaner. Ah, there we go. So we have labels, then values for experiment A1, experiment A2, experiment A3, etc. Great. So now we have numbers. Okay. With that data frame, we would like to pull out some bits of information from this. So let's say that we wanted just the 5th row from the experiment table. We did some of this with the matrix yesterday, didn't we? Yeah, so I'm going to blitz through it. So if we look at just row 5, which is what this 5 comma means, what would it mean if I put comma 5? Yeah, right. If I said comma 5, that would be the 5th column. 5 comma is the 5th row. We note that the software still comes with labels. See that? So the software, R remembers that this data table's first column is labels, its second column is experiment A1, and then these are the values for the 5th row drawn from it. That's very helpful. All right, let us instead grab out only an individual cell. We want to grab out the 5th row and the second column together. All right, we have just that one solitary value that comes out from the 5th row, the second column. All right, sometimes in data frames, we want to grab things by name. So I've mentioned the bracket, the square bracket operator, the index operator. We can use this $sign operator because our columns have names attached to them. This is not a matrix, it's a data frame. This data frame has named columns. Could you also just say, I want the 5th element from this? You can. That also works. So those two should give essentially the same result. There are some reasons why they're different. The alternative syntax I used was to grab the 5th column. Okay. So we also occasionally want to pull out data that meet a criterion. And the reason I presented it today is that we've already looked at criteria for if and for while loops, right? In both cases, we had a criterion that decided what we were going to do. In the same way, we can specify that we want to pull out from the experiment table all those data points where, all of those items where experiment A1 had a value less than 0.5. Because you are generating your numbers differently, because you're generating the numbers on your computers, my random numbers are not the same as your random numbers. Okay, so I'm now going to run just that subset command. So we started with experiment table. We can check the dimensions on experiment table by using the dim command. It tells us, oh, it was 26 rows in height and 7 columns in width. But now we've run this subsetting function, and we stashed its result in sub-experiment. So let's take a quick look at the dimensions of our sub-experiment. In my case, I got 9 rows out and 7 columns wide. So in these, all of the experiment A1 values should be less than 0.5. Here's the experiment A1s. Are all of these less than 0.5? For row 1, yes. Row 2, yes. Row 3, row 4, row 5, row 6, etc. All of those are below 0.5, which is why the software returned these rows for me. So very frequently, you're going to pull out if you were in Excel and you were trying to find all the rows of this table you were looking at that were below 0.5, you might sort the whole table and then count off which ones fell below that number, right? So it's easy to have something like a subset command to generate a subtable from the big table. It's a handy feature. So I ended up using subset a whole lot when I was a PhD student, largely because I didn't know how to use the index command very well at all, but it's helpful to have stuff like that. All right. We have one other thing that we want to talk about today, and that is defining our own functions. So we have already used piles of functions. Subset, for example, had the parentheses that we use to parameterize something. Today, I want to define our very own function, and we're going to call it Pythagoras. The reason for this is that we are going to compute distances between 2 points in an xy plane, right? So we're all drifting our minds back to high school again. We have our xy plot, and we have a couple points there. We want to find how far apart point 1 is from point 2. Everyone remember that? So you can think of that as a right triangle, right? You drop a line down until the y value of that line has reached the second y coordinate, and then you can draw a line horizontally over to that point. So that's a right triangle connecting those 2 points. And as we remember from our algebra classes long, long ago, if we square the 2 horizontal and vertical sides of that triangle, add those squares together, and then take the square root, we get the distance between them. Everyone remember that? That's good. This is a good class. All right. I got into trouble once teaching this in China because they don't call it the Pythagorean theorem there. They call it the rule of right triangles. See, somebody in China independently discovered that a long, long time ago, probably a much longer time ago than even Pythagoras. So they don't call it the Pythagorean theorem at all. We talk about decolonizing our education. That's decolonizing our education right there. We learn something when we teach in lots of places. Okay, so we're going to need to pass in two values for x, 2 values for y, and from that we're going to deduce the distance between those. Now, we're going to use what seems a little redundant, the function, because the function is going to let us define a function. And we're calling our function Pythagoras. Pythagoras becomes whatever function returns from this block of code. We're going to pass in an x1 value, a y1 value, and we should also pass in an x2 and y2 value. But look, I've added something unusual here. I've said x2 equals 0, y2 equals 0. Are you familiar with the term default? Not in the sense of defaulting on your car loan. None of us should ever do that. That's very bad. A default value is a value that a variable takes on if nobody specifies what it is otherwise. Right? So if the user, for whatever reason, decided to pass us only one point, one pair of coordinates on the xy plane, we're going to specify that the other point they meant by default was the origin. So if they pass in only one value, or one xy coordinate, we're going to compute how far is that from the origin. If they pass in 2 values, we're going to cheerfully use whatever their second point is. All right. First, we're going to compute how far apart the x values are. Now I note that I've used yet another function that you haven't seen before, but hopefully it seems pretty familiar. This is the absolute value function. So, if I were doing this in math, I would probably say something like, what is the absolute value of minus 5? But look, that's not a syntax that R understands. If, on the other hand, I say, what is the absolute value of minus 5, it's happy as a clam. Okay, so sometimes the math looks a little different because of because of syntax in R. We're going to compute the absolute value, the difference between the x's, the absolute value difference between the y's. Here we're going to square each of those independently, add those together, and then use yet another function that we haven't seen before, the square root function. I think everyone gets what that's doing. Finally, we're using another function to specify that this function doesn't just run quietly on its own, it returns a value as well. So we're going to return this distance that we computed by square rooting the sum of squares. All right, so I'm going to now run this stuff. Boom. Now what does it tell us? Does it tell us function created named Pythagoras? It does not. It just did it. So again, it's being the strong silent type for us. So let's now try typing Pythagoras. It's very easy to type, isn't it? And we're going to start with an easy, a relatively easy problem here. I want a coordinate 3, 4. So which one? What is 3 going to set? X1, because it's the first one listed. The 4 is going to set Y1. What about X2 and Y2? They're not set here. Does anyone know what this value is before I hit enter? Everyone remembers from algebra class, I'm sure, that if you have a right triangle with sides 3 and 4, the other side is 5, right? Does everyone remember what you get if you have 5 and 12? Okay, I was totally the math nerd in high school. You can tell this, right? How did I end up in biology? They didn't kick me out. How's that? All right. Okay, so Pythagoras works as it's intended when we give it just one coordinate. Let's now try giving it a second pair of numbers. I'm going to make this 6 and 8 because I'm just that way. Does anyone know what this is going to return? It's 5 again. All right, so 6 is 3 away from 3. 8 is 4 away from 4. Therefore, it's just the same triangle all over again. Yeah, just except this time further away from the origin. Okay, so that's grand. We note that it is a return value. So I'm going to say C. I'm going to repeat that last command, return to the start of the line, and I'm going to say C equals the Pythagoras of 3, 4, 6, 8. So it captured whatever came back from Pythagoras in the C variable, and if I type C by itself, I get the number 5 again. Okay, so we've created a function. It has default values for 2 of the parameters you could feed it. It returns a distance, and we can capture that in a return variable by saying C equals that function. There are lots of times when we do stuff like this, like you want to compute a dot product or something, and instead of typing out that code every time, it helps if you can just define the function and then call it in other code. So Pythagoras is now available for me to run. But what happens if I exit R? Is Pythagoras still there for me? It's not. Now you remember when you exited R the first time, it asked you, do you want to save your workspace? If you save your workspace, Pythagoras is still there for you. Otherwise, you're going to have to re-enter that code at the start of whatever script you're going to use that runs it. Okay? Great. So we've seen a lot of cases where a Boolean condition was required to decide whether to keep running that code, or to decide a conditional execution to decide if this is true, then execute that code. Otherwise, don't. You've seen for loops for iterating through a set of items. You've seen the subset function, which I introduced just because I think it's really lovely and, again, uses Boolean conditions. And you've seen how to define your own functions. So you're getting to know how to do quite a few sneaky things in this language. We are going to continue with that language tomorrow, and I think we might actually be doing some plotting tomorrow. So if you haven't already installed the ggplot function library, I need you to make sure you've done that before tomorrow, because after all, we can't count on having internet services. But with that, I believe we are done for today, and I will look forward to seeing you tomorrow morning at 9. Thanks.